Welcome, everybody, again. This is the third session, the third time we meet online to solve some interesting exercises. At the moment, we are concerned with complex numbers. Of course, the idea was to get this done last week, which we did not really manage, but anyway, I'll return to this exercise, and then after a while we'll try to proceed to exercise sheet number 3, which is new, and it's also a new topic, as you know, about systems of linear equations. So we take our time as much as we need, and we'll see how we proceed during the next weeks. So if you remember, I hope you remember, we found out that in the first two cases, this has not directly anything to do with complex numbers, really. It's given in the complex form, but just regarding the symbol z for a complex number anyway. But we found out that this is a very well-known case where the so-called discriminant is 0, so we get one double solution that was done, and in the second case we have two regular simple solutions. Everything fine, but now the most interesting case, of course, regarding complex numbers is case number 3. And if we look at this, the first thing to do is, at least it's possible, it's not necessary, but it makes sense, to multiply the whole equation by 2 so that all the coefficients get whole numbers. This is what I do first, and then we find this equation, which reads z squared plus 2z plus 2 equals 0. It's striking, probably without using any formula or equation, it should be striking that probably there is not even a single real 0 to this polynomial. So the equation would have not even one solution in the domain of real numbers. Now, since we allow for complex numbers, we look at the discriminant and we find that this time it's always this, the discriminant is always b squared minus 4ac. But this time, if we put in the values, we find that b equals 2, 2 squared is 4, then minus 4 times 1 for a and 2 for c means minus 4 times 2 is 8. So we have 4 minus 8, which is negative 4. So the first time here, we have a negative discriminant. And we all know, at least by using the classical, here you see it again, the classical solution formula for this type of equation, we get the problem that the square root of a negative real number is not defined in the real domain. So now comes the trick. Let me call it a trick. But it's a legal trick, if you want. Okay. The trick is to transform this solution formula like this. So what do I do here? I keep it. It's still minus b plus or minus, and then the square root of the discriminant. I'll explain this in a while, and then divided by 2a. So here the point is, since I know this time, or as soon as I know that the discriminant is a negative real number, the only way to take the square root is to first remove the minus sign. So if I write minus d inside, it means, in this case, it means minus 4, which is positive 4, so it's no problem to take the square root of 4. And the positive root of 4 equals 2. That's fine. But how do I get this minus here inside? And there, the legal trick, as I said, is like I have square root of, I just use this abbreviation for the discriminant, okay, so that I don't have to put these terms all the time. Actually, it would, first of all, there would be square root of d. That's usual. But then I say this is the same as minus d, like this. And then one of these minus signs, now for the trick, is replaced by j squared, because we all know that j squared is defined to be -1. So that's allowed. So far, it's really clean. And now in the next step, I would separate this. I use regular calculation rules, which have been valid all the time, and they remain valid. And then, so I can split this expression to square root of j squared times square root of -d. But please note that -d in this case, in our case, is a positive value. That's the reason why we're doing it, to get a positive radicand inside here. Now, a little problem is, okay, actually we have a case, where is it? You see it here. We already have two cases to consider, like plus or minus the root of the discriminant. This is what we get because it's a squared equation, and we all know that we always have two different, namely the positive and the negative square root as a solution. This is what we know from the real domain, and it has been confirmed over and over again. So this is well known. We also know that the square root symbol always denotes the positive root, and to get the negative root also means we have to make this, to make up for these two cases, plus or minus. We all know about this. And please don't mix it up. The minus sign here has nothing to do with a negative radicand, which makes real hard problems in the real number domain. That's our problem, a negative number here inside. It's not our problem to have these two cases, plus or minus. These are valid all the time. Now, if I do the same here, if I put this plus or minus before, then a little bit, well, a certain caution is necessary when we take the square root of j squared. We could just simply say, okay, we know j squared is -1, and, or in other words, the square root cancels this, the square sign. So we could just say this is j. This is a little, it's not wrong, but it's not really correct. The correct result would be plus or minus j. You remember, not only j squared equals -1, but also minus j squared also equals -1, because the minus is of course removed by the square sign, but j squared is still equal to -1. In other words, the real number net -1 also has two different square roots. Now it's not so easy to talk about the to call these two solutions the positive and the negative square root. And this has been done for a long time in the real domain, but as soon as we introduce complex numbers, it makes not so much sense anymore to talk about positive and negative numbers, because suddenly we have a whole range, a whole infinity of arguments for complex numbers, which is, you could say, the new sort of sign. Okay, so in contrast to a negative or positive real number, we have a whole range of arguments for complex numbers, which is an infinity. I'm talking about the the direction angle to the direction of the positive real axis. In so far, it's not really allowed to say we decide to use the positive solution of this equation. I like to say that the positive square root of j squared equals j and not minus j. In the end, it doesn't matter. That's the good news. It doesn't matter because even if I would allow for two different cases here, I already have two different cases here. And if I put another case distinction, that's what I meant before, I could do this. I could say, okay, now at this place it's plus or minus j. It would turn out that the combination plus or minus and again plus or minus allows for only two possible outcomes, which are plus or minus. Okay, so that means in the end it doesn't matter, and it's enough to write down plus or minus j times square root minus discriminant. That's what I'm doing here. Sorry for the complicated explanation that was, because it's really a little bit difficult to argue in the moment when you draw the square root of j squared. But in principle, I think that you see what I'm doing here. Okay, so it should work, and it does, because now we can just put in our values, and we have, of course, 2 for b. Then that's already done. The discriminant is -4, and a equals 1. So we get -2 plus or minus, and then j times square root of -4, which is square root of 4, and actually is +2. But of course, then we have the case distinction plus or minus 2j, and below it's 2 times 1 equals 2. Reducing to lowest numbers, we get -1 plus or minus j. The interesting fact about this result is, firstly, that both solutions are real complex numbers. I mean, real complex sounds paradoxical. No, what I mean is they are not purely real and not purely imaginary, but they are mixed. Okay, so they in German we say these are echt complex. So but it doesn't sound good to say real complex, fully complex, whatever. Okay, so but anyway, the more interesting result is that -1 plus j is one solution, and the other solution, -1 minus j, is the complex conjugate. So these two solutions are complex conjugates with respect to each other. And that's a fact that this is not by chance. You know where it comes from. It comes from the solution formula. And actually, this takes place every time you solve a polynomial equation that contains exclusively real coefficients. That's a very important feature, okay? So the equation itself allows for complex numbers, but all the coefficients are real numbers, which are 1, 2, 2 in this case, okay? As soon as you put, however you do it, as soon as you put something complex inside here, for example, if the constant here, sorry, it doesn't work now, gets 2j, which is imaginary, suddenly you can still use this formula if you know how to do it, but it's a little bit there are better methods then to do it, because it's necessary then to put complex numbers inside this solution formula, even here and inside the discriminant. So that gets a little difficult to handle, but it's possible. Anyway, I can guarantee you that suddenly the two solutions that you find will no longer be complex conjugates to each other. This is only the case if every single coefficient is a real number. So this is a very general theorem also. Here I wrote, perhaps you know this, if the word if written with double F in mathematics is sometimes used for if and only if. So this is an abbreviation to say if and only if. All coefficients are real, element R, then complex solutions are pairwise complex conjugates. So this holds even for any higher grade n. So even for such an equation with grade 6, grade 9, whatever. And that's why I say pairwise, you know, because I could have more than two solutions here. I could even have some of them are real numbers and some others of them are complex, but you never get a single complex solution then in this case, okay, with real coefficients. You always get complex solutions pairwise and even pairwise complex conjugate. So that's just an important fact about the fundamental theorem of algebra inside complex numbers. So I see, as usual, it takes me too much time to explain. Anyway, we will proceed to this one shortly.